In this session, we are going to discuss the VGG architecture. In our previous session, we have had discussion on AlexNet, which is considered as the grandfather of modern convolutional neural networks. VGG is considered as the father of modern CNN architecture design. It was developed by the Visual Geometry Group at Oxford University and in 2014 took first place at the ImageNet Large Scale Visual Recognition Challenge. VGG is known as for its simplicity and depth. Before VGG, most neural networks sees a variety of layer sizes and types, making them hard to scale and generalize. VGG introduced a more uniform structure using small 3 by 3 convolutional filter and stacking multiple layers. This approach allowed the neural network to learn complex features with few parameters, enabling it to the scale of deeper architecture. As you can see in this picture, the VGG architecture introduced several fundamental design principles that have impacted today's research in deep learning and computer vision. VGG showed the increasing depth of neural networks by stacking more layers, it can lead to improved performance. So, by demonstrating that increase in depth of the network with more layers could lead more improved performance. Now, in this picture, as you can see, power of depth, VGG demonstrated improved performance through the increased network depth. And second point, influence development of deeper architecture with complex building blocks. The next thing is these deeper architectures often use modular building blocks to manage the increased complexity and to facilitate efficient training of deeper networks. This insight has driven the development of even deeper architectures such as ResNet and DenseNet, which employs skip connections and dense connections to throughout the entire network. Now in next picture, we can see the use of small filter. So this differed from some previous architectures which use large filters. VGG demonstrated that the small filters could efficiently capture local information while reducing the number of parameters and computational complexity. The next is a practice that has become standard in modern architectures. The use of smaller filters help reduce number of parameters, computational complexity, while maintaining network's ability to capture complex patterns. VGG also introduced the concept of stacking multiple convolutional layers with the same filter size, which could be seen as the building block for constructing deeper architecture. These blocks, as you can see in this image, these blocks made it easier to design the network of varying depth by simply repeating and stacking the blocks. VGG, it is used a consistent pattern of convolutional layers with the same filter size 3 by 3 throughout the entire network, followed by its pooling layers. This homogeneous structure can be seen as a series of modular blocks, making it easy to adjust the depth and complexity of the network by simply repeating and removing these blocks. So, this structure allows researchers to treat the convolutional blocks as the interchangeable components, making it easier to experiment with different networks, depth, and configuration. Now, here is the uniform architecture that we can see a breakdown of the VGG architecture 16 layer by layer. First, we start with the input layer, as you can see in this image. Then, as you can say, it is similar to the other architectures. The input layer receives the raw pixel values of the input image and provides it as a starting point for subsequent layers. This is followed by the convolutional layers. The next is VGG16 has 13 convolutional layers labeled con1 underscore 1 to 1 con5 underscore 3, as you can see in this image. This use 3 by 3 filters to extract information from the input maps. The max pooling layers are there for reducing feature map size. After every two convolutional layers, the max pooling divides the feature maps into areas and preserves important features by keeping the highest actuation value in each area. The fully connected layer, well, VGE has three of them, and this extract features and classify the image. The VGG16 architecture uses small filters and deep convolutional layers to capture complex features. The pooling layers reduce dimensionality while retaining important information, and the fully connected layers convert the high level features into class probabilities. The introduction of this modular design is something that is stuck with deep learning researchers since the introduction of VGG in 2014. So we have covered all the aspect of VGG16. Now in the next session, we are going to discuss our next convolutional neural architecture, which is ResNet.